Hi, everybody. Welcome to class today. Today, we're going to complete one subtopic of parametric equations, namely the thing with projectile motions. We're going to see how you can calculate out an unknown angle if you know what the starting velocity is and you know what uh, horizontal displacement is. And then we're going to begin a very difficult section of precalculus, which is where we learn how to create the equation of a parametric equation. If I give you like a graph, and the graph can be pretty complicated looking, and it has a lot to do with like circles, where there's a point on the circle while the circle is moving around and the path that that makes. So those are some things we're going to learn about this week. And it's one of the trickiest weeks, actually, this topic. But what we start with is not going to be such a tricky question. So the warm-up question is, what's the parametric equation, or sorry, what would be the graph of this parametric equation? X equals cosine t, y equals sine t. And you could type some stuff into the chat. You can get more detail than just like one word. So type some stuff about what should the graph of that look like. Okay, I see a lot of good comments. Unit circle, centered at the origin, radius of 1. There's another detail. Um, there's another detail that you can include. It may seem like if you have the center, and here I hear a circle going counterclockwise. So somehow, if you watched it get drawn in slow motion as t went from 0 to 360, what would the first point that got graphed be? Because you could start, in theory, anywhere on the circle when you say a graph going counterclockwise. And Leith says 1, 0. And that's right. So let's take a look. So here's the situation. That's what happens. And if you want to see that happening, I'll show you how in your graphing calculator we can take a look at that. Let's see. Okay, so here's the emulator. So here I have cosine t, sine t. Notice how over here I've got this like lollipop thing. That makes it graph a little bit slower. Before I graph it, there's a few more things I have happening. I am in degree mode. You could be in radian mode if you wanted, but I happen to be in degree mode. So for my window, my T max is 360. If you were in radian mode, your T max would be 6.28. And my T step is about 7.5. If you're in radian mode, your T step should be, about 0.1 or something like that. Now, because this is a unit circle, I don't need my graph to be so big. So I made my X min and X max -5 to 5. And my Y min, Y max, I actually made -3 to 3. But then when I said zoom square, which is number 5, it makes everything so the units agree with each other. So it changes the window. And take a look how nice my graph will look. And you'll see it go counterclockwise as predicted. Well, starting with this equation, we're going to see how altering the equation a little will make it go clockwise or start from a different spot or be on a bigger circle, or the center of the circle will change to a different thing. And then starting tomorrow, what if the circle were moving while the point was going around the circle? That makes some pretty unusual looking graphs. So those are coming. I also want you to know that it's not an obvious thing to do, but I wanted to show you how in Desmos, which is a really good sort of graphing calculator, um, here I have n, which is actually, which is the t value, and as I move n from 0 to 2 pi, it goes around. The way I made that happen, I think I need a new window to show you how that happens. Okay, so on Desmos, just to show you how this works, to create a parametric, you go like this: cosine t, comma. So your x, you don't write x equals and y equals. You actually create like a point. Oh, I'm going to have to switch the window that I'm looking at. Hold on a second. Sorry, everyone. Let me change that window. Chrome tab. Here we go. Sorry about that. So what you do is you come over here. I'll erase that. And you type cosine t, comma sine t. That's how you put a parametric equation into Desmos. The x equation you put in as the x coordinate, and the y equation you put in as the y coordinate, and then you change this t to 0, 2 pi, and you see the circle. But what you don't see is the order that the circle got graphed in. In order to do that, you have to actually not use t, but use some other variable like cosine n, comma sine n. And that one lets you add a slider. When it's t, it assumes it's a parametric equation. But for this one, you add a slider, and you make the slider. You click on the gear here, and you make the slider from 0 to 2 pi step 0.01 or something like that. And now, if I bring this back to 0 and I hide this one, you can see that it will show the order that the points got drawn in. And I like to have both up actually at the same time so we can see the curve at the end, plus we can move this slider from left to right. Okay. So that's how you do it in Desmos, and you can do it on the graphing calculator also. Okay, so I haven't looked at comments in a bit. Hold on a second. I'm sure there's people telling me that I'm on the wrong window. No, I haven't seen anything. Okay, let me go back to the iPad. Okay, here we go. I'm sorry I don't have a better system. I was watching some, math guy who has a weekly or daily show that he does on the internet, and it was pretty cool. It was like him standing there, and then in the background, as he wrote on like some kind of tablet, the text came up like on the wall behind him, and he showed us that he has like a blue screen. He has a whole studio going on. Anyway, I don't think I'm going to be able to get anything like that going anytime soon, but I'll do the best that I can. Let's take a look. Here is the third scenario that I didn't show you the other day. In this scenario, we've got, we know what the initial speed is going to be. And for some reason, the theta did not copy over properly. What must theta be? So we know what the initial speed is, 49.2 feet per second. And we know the initial height is 0. This question is really hard if the initial height's not 0. So when I do it, the initial height is always going to be 0. And we want it to land 65.2 feet away. And we want to know what should the angle be. And this would be like in a real life situation, like a cannon or something like that, where you don't have control over how fast what the initial speed is, as opposed to like if you're shooting a basketball, where you do have control over the initial velocity. So here, the initial velocity you have no control over, or if you're at a carnival and you have to shoot water into the clown's mouth and you have like a water gun, it's the angle. That's the only thing you have control over. Now, we're going to see that there's actually two answers to this question. You remember the other day, people thought maybe there was two answers to any question, like of how can you, if you could pick any v0 and theta, and you have to hit a target, there ended up being infinite answers for that. Whereas the other scenario where you're told what the angle is, and you have to figure out the v0, well, there's only one answer for that. But this one, there's not infinite answers, and there's not one answer, but there's actually two valid answers. And I'm going to take you through this problem. It is pretty, it comes out pretty ugly, so I'm going to take you through it. But it does start with the two equations, y equals negative 16t squared, in this case plus v0, which is 49.2. We don't know what theta is, so we have to leave it like that. And I don't need anything over here like the plus 0, and that's going to actually make this a lot easier, although still hard, even with nothing over here. The initial height is 0. This question is still pretty hard. And x is 49.2. Is it possible? Oh, wait. Oh, it's blocking the equation. Let me see why that is. Oh, this weird thing? What is that? Oh, I know what that is. Sorry about that. There we go. That thing is because to get an iPad onto my screen, I had to use QuickTime Record. It's complicated, so I'll have to be aware of this thing. Thank you for pointing that out. Okay, so there's the equations. Now you can see the problem here. There's so many variables. There's a theta, a t, there's an x, there's a y. There are too many variables. So what you do is we take the x equation and we rewrite it as t equals 65.2 over 49.2. Oh, and now I bet I have the same problem. Hold on a second. I know how to fix this. If I make this window much larger, it will appear to shrink the other thing, maybe. Okay, would someone tell me how, does that look better? Okay. Okay, I thought I could make that window nice and small so it wasn't taking up so much room and no one would know, but this thingamajig doesn't, it stays the same size no matter what you do. So the bigger I make this, the smaller that thing goes and the less intrusive it is. Okay, back to this. It's 65 over 49.2 cosine theta. Now, when it achieves, hold on a second. Yes, I forgot to do, remember, we want the x value at the end to be 65.2, remember over here? So I make that 65.2 because that is what my goal. But that's also when y is 0. So basically, when this thing hits the ground, which is at y equals 0, whatever time that is, y is going to be 0, while x is going to be 65.2. And that's why when I divided both sides by 49.2 cosine theta, we got t equals that. On the other hand, the y equation is now 0 equals, and check this out. This does not look fun. Plus 49.2, that's V0, times sine theta, times t, but t is again this pretty ugly expression. Okay. And that is looking pretty bad. You might be looking at that, maybe you see this sine, or maybe you're thinking there's a tangent here with the sine over cosine, but actually there's a really sneaky way out of this. Anyone know what a nice next step might be? Someone mentioned that substitution. Yeah, go ahead.
If you multiply, I think for the VO sine that theta 2, if you multiply 49.2 by t, you end up with 65.2.
Oh, are you saying, wait, if you multiply 49.2 times cosine theta, you get 65.2? But what would I do in this?
Yeah.
So are you saying there's some kind of substitution I could perform?
Yeah, I think so.
What would you substitute?
I'm not sure.
Okay, this is a pretty good idea. There's going to be something actually even easier than that. It is going to be to multiply both sides of this equation by 49.2 cosine theta squared. See how this denominator and this squared here? If I were to multiply both sides of the equation by 49.2 times cosine squared theta, the left side would still be 0, because 0 times anything is still 0. But the right side would turn into minus 16 times 65.2 squared. So just make a note, I multiplied both sides by 49.2 cosine theta squared. So this first term, you just lose the entire denominator. Now this other term, when you multiply, I'll write it all out first. So it's 49.2 sine theta 65.2. It was originally this, but now I'm multiplying it by 49.2 squared cosine theta squared, or cosine squared theta. So what happens is that this 49.2 can cancel out with that 49.2, and this cosine theta can cancel out one of those cosine thetas. And if I move this minus 16 thing over to the other side, I get 16 times 65.2 squared is equal to 65.2 times 49.2 squared. This sine theta is still there. And I suppose I can cancel out one of these 65.2s with one of those to make it even easier. Now, looking down the road, this thing looks problematic. But let's see what ends up happening next. I divide both sides, so I end up with 16 times 65.2 over 49.2 squared equals sine theta cosine theta. And this becomes 0.43096 equals sine theta. And there was if you did the homework, I know it wasn't due, it's not due yet, but if you did, you might have seen, what is this cosine theta, sine theta, cosine theta? How do we deal with that? There's too many thetas. Anyone know what the good next step is? Yes, the sine 2 theta formula. So let's refresher. That sine 2 theta is 2 sine theta cosine theta. So what I like to do is multiply both sides by 2. 0.86 whatever is equal to 2 sine theta cosine theta, which is equal to sine of 2 theta. So now I end up having just, I have 2 theta, but 2 theta in a different way. First I had 2 thetas, literally, and now I have 2 theta in that way. And I could work with that equation because I solve that equation the same way I would solve like sine x equals 0.86. I would say alpha, reference angle, is sine inverse of 0.86, which is 60 degrees. Or, which means that 2 theta is 60 degrees, which means theta is 30 degrees. But I said there's 2 answers. And here's just one answer, 30 degrees. Where's the other answer coming from? You could type into the comments. Well, it does end up becoming the complementary angle, but why is that? What lets me do that? Because 60 is the other answer, but why? There's a little step that I left off. 180 minus 60, that's right, because when you have the reference angle, sine is positive in quadrants 1 and 2. So 2 theta 60 is the reference angle, so 2 theta is either 60, because this 0.86 was positive, it's quadrants 1 and 2, so it's 180 minus 60, which is 120, and theta equals 60 is the other answers. The other answer. So there are 2 answers to this question, and I'm going to show you that it works by bringing back the actual simulator. Okay, so here's the simulator all set. I have it in, it's set perfectly. It's just this David statue, he doesn't move. And you can, when you try to like cannonball him, he doesn't get destroyed. I don't know exactly what he's doing there. Anyway, if I turn this to 60 degrees or first to 30 degrees, we see that it lands right on there. And if I change it to 60 degrees, it also lands right on there. And this thing is kind of fun because you could pick other stuff, like you could set a piano there, or a human. What happens there? This little guy. Oh, he just lands on his feet. So you say no one gets hurt. And as far as hitting this David, maybe I'll hit him with the piano. See, David statue does not get harmed. Okay, so that completes the projectile motion part. But now we're going to look at, in preparation for something that's really difficult. So let me come back to the smart board. Okay. I want to see if it's possible to create a parametric equation that the things we need to know are the center of the circle. So the center of the circle is 0, 0. We need to know the radius of the circle. In this case, the radius of the circle is 2. We need to know the starting point, which in this case is 2, 0. And we need to know whether it's going clockwise or counterclockwise. You need to know all 4 pieces of those information to create this equation. Does anyone want to type in what alteration you think you need to make to the original equation in order to make this happen? Remember, before it was x equals cosine t, y equals sine t. And Leith is right. By putting a 2 in front of the cosine t and the sine t, it will cause it to have radius 2 instead of radius 1. Now, Ariel, center, radius, direction, and starting point. 4 things. So this is how you can get a larger circle to happen. And if you want to see that in action on your graphing calculator, you can easily come over here, window. If I come into my equation here and I say second insert 2, second insert 2, you will see that it makes a larger circle as expected. Okay, the next thing I want to see is what alteration do we need to make to this equation to make it start at some other location. So here, let me bring the iPad back. So now I want to do just what I did, but I want to make a slight change. It's still going to be circle still centered at 0, 0, still going counterclockwise, still radius of 2, but now the starting point is now 0, 2 instead. Oh, someone made a comment. Let's see. Yes, and I see the answer there, which is the only difference is we put a plus 90. So the reason why this happens is when I put 0 in for t, it does cosine 90 and sine 90, which are 1, 0, and that's why it starts over there. So I'll just say this is whatever the starting point is, because it's starting at sort of the 90-degree spot, that's what you put after the t. If I wanted it to start over here, I would put a plus 180. If I wanted to start here, I could put plus 270, or I could even put minus 90. Someone mentioned about switching sine and cosine. Well, switching sine and cosine does also do some of this stuff, make stuff go potentially counterclockwise, but I'm going to advise against it. We're pretty much always going to put x with cosine and y with sine, even though it's true. When you switch them around, the reason why it works is that like sine is cosine of 90 minus x, and that's kind of why switching it makes it work also. But we're going to be better off pretty much always putting x with cosine and y with sine. There's other things you could do, like put a negative in front of the y, like over here. But I'm also going to advise you not to ever do that, but to always have the same number in front of both of these equations. And if you want to see that one in action, I can show you that. We're almost done for today, so we're in really good shape. I think there's 2 more scenarios. Let me bring up. So if I come over here and I throw in plus 90, and over here I put the plus 90, and if you take a look at the graph, you will see it does indeed start at the point that we expected it to. This is, well, here, let me bring back the smart presenter. Okay, the next scenario is how to make the point go. Let's say I want to start over here, but I want the point to go clockwise instead. Actually, I'm sorry. Can I not do that one yet? If you don't mind, I'd like to start with the point at the typical spot, but going clockwise instead. The radius is 2, the center is 0, 0. This point is 2, 0. And I mentioned it the other day, but at that time you didn't have like a lot of context for it. So maybe now you do. Yes, Willis, that's right. By replacing theta with negative theta, that will cause it to go. So this is 2 cosine negative t, and y equals 2 sine negative t. That causes it to go clockwise. And this is because when you put in 0, it still does the 0 point, but when you put in like 30 degrees, it does cosine negative 30, sine negative 30, which is going to be a point over here. So as the t gets bigger, the point that it's graphing is negative 30 degrees. And that's how we make it go clockwise. And then we can kind of mix and match. We can go from like a different point there by doing something like x equals 2 cosine negative t plus 270 or minus 90. Y equals 2 sine negative t plus 270. Or if you like, you could put a negative 90. And yes, there's other ways to do this with switching sine and cosine around, putting a negative in front of the 2, but you're better off. It could be negative t minus 90. If you wanted to like factor out the negative, you could, if you wanted to call it negative t minus 90 and factor out minus t plus, I'm actually not going to do that ever. So you won't have to worry about that. I'm not going to factor out the negative sign, but it is because when you put 0 in for t, negative t is still 0. So it's going to become cosine 270, sine 270. Okay, and the last situation is this. Oh, someone asked if it's counterclockwise, shouldn't theta be, did I say counterclockwise? Sorry, I meant though, this one is clockwise. So when it's clockwise, the theta is negative, and when it's counterclockwise, the theta is positive. The thing every example we've done so far had in common is that the center was at 0, 0. To end off today's lesson, we're going to look at, is it possible to get the center to be something else. So here's one where the center is now 5, 3. And the starting point is over here at 7, 3. And I'll tell you this one's going. Okay, why doesn't everyone think now? What alteration has to be done to this so that the okay, I see some people say add a constant, replace x. Z says add a constant. What do you mean by that? So what would the equation be? You say a constant. That's right. For the x equation, you would put a +5 there. And for the y equation, the +3. That's all that needs to happen, because then every x value gets increased by 5 and every y value gets increased by 3. I can summarize this by saying x is equal to r cosine. Hope you know, I'm gonna write like plus minus t, depends on what the situation is, plus, I'll just say theta, plus h, where h is the x-coordinate of the center. And this takes care of every scenario that we have. So this is at least every scenario where the center of the circle is a constant. It doesn't, like the circle, the center of the circle is not moving, just the point on the circle. But tomorrow, and actually for the next 3 days after today, the center of the circle is going to be moving, and this is going to make some really unusual curves. Let me bring back the graphing calculator. Okay, here's the graphing calculator, and you can see that if I take this equation, let's just say I take this equation and I add on the 5, and I add on, was it 3? This one, because the plus 90 is still there, is going to start at the top. But watch the graph. Well, too big for the graph. I could zoom. Is there an assignment? I think there is. Here, I'll zoom out. Oh, the name of the assignment. Yeah, no, it's just assignment for, just skip to assignment 44. So you see it did create. So, and that's how you make that happen. And let me also show you, because I'm going to share with you the Desmos activity, or sorry, the Desmos thing. If I come over here and bring back Desmos, parametric circles, we can, let me get rid of all this stuff. So here I have the equations, and I move this thing around, but you can actually mess around. You can change the radius. This a value just switches from -1 to 1, and the only difference there is if it's at -1, you'll see it will go clockwise. And I can mess around with the c value. That's the plus theta. So you see when I change that, I could start at a different point, and then the h and k are the center, so you can mess around with those. Okay, well, I want you to get really good at these, because tomorrow we look at what happens when the circle starts to move while the thing moves around on the circle, and it's going to make some really unusual curves. Let me bring back the iPad. And let me stop the recording.